So thank you to the organizers for inviting me here. So I'm a computer scientist interested in the theory of algorithms, and this talk is going to be about a subfield in computer science which could be called running time analysis or complexity analysis of so-called randomized search heuristics. This is just an umbrella term. Randomized search heuristics could be evolutionary algorithms, but also other methods. Christos Papadimitriou mentioned some of them yesterday: local search, simulated annealing, and collinear optimization, particle swarm optimization. They work with a set of solutions to some problem, and then they typically would run in rounds by initializing and then selecting good solutions according to some fitness, and then varying them. That could be mutation or crossover, and then they select again, and it goes on like this. And the purpose is here optimization. So classical optimization, you have some objective function, f, which maps solutions to some value. So the search space could be anything you would like to optimize. So you would like to find the shortest path in a graph, then the search space would be the set of all paths. So this is the setting: minimize, or generally optimize some function. And such methods would be applied in practice if you don't have a specific problem-specific algorithm. So what is done in this area is trying to understand these methods using tools from computer science. And then one would be interested in, as you would analyze a randomized algorithm, you would be interested in studying the expected optimization time. It's a randomized thing, so most of the time you would be interested in the expectation of the running time. So that means the time until this algorithm has found an optimum. And this was actually already done 25 years ago, when people looked into simulated annealing and tried to derive the time complexity of simulated annealing for finding maximum matchings in a graph. So from roughly 2000 on, this field got momentum, and people were using and studying other kinds, in particular evolutionary algorithms, from this perspective, using the techniques or adapting the techniques from classical randomized algorithms. And today we have quite a lot of interesting results which tell us on which problems evolutionary algorithms and other search heuristics are efficient on and which not. This holds particular for combinatorial optimization, where this search space here is a discrete one. There's still one major challenge in this area, or the analysis in this area is facing one major challenge, namely that even very simple looking settings, very innocently looking settings, can be surprisingly hard to analyze. So one intuitive reason for this is since, well, these methods, they were not designed with analysis in mind. When people came up with evolutionary algorithms in the 1960s, they were interested in mimicking evolution, survival of the fittest, and they did not have a running time analysis in mind. This is different when you are, as a computer scientist, designing an algorithm. Then you would be, when designing this algorithm, also be interested in making this algorithm amenable to a running time analysis. So this causes a lot of problems. And for today, I would like to show you some of the results that can be obtained in this area, also techniques, and maybe discuss what can be achieved here afterwards. So my talk is divided into 3 parts. I will introduce to you one important technique for the analysis of randomized search heuristics, namely drift analysis. I'll show you one application to a problem, a benchmark problem, so to speak, which could be called weighted hill climbing. How good are EAs at optimizing linear functions? Can we get any running time bounds here? And in a third part, I am going to discuss whether this drift analysis technique could be useful for other problems from classical computer science. So nothing about randomized search heuristics any longer, but a classical computer science problem. So let me start by explaining what drift analysis is about. So first of all, when we take an evolutionary algorithm, we say it's a randomized algorithm. It has some input, it has some output, it will stop after a while when we have a stopping criterion. So in principle, we should be able to define something that is called running time, and that would be the time until this algorithm has found an optimum to the problem, assuming a discrete problem. Or when the problem is very hard, an NP-hard problem, then we might be interested in arriving at a good approximation of the optimum. Evolutionary algorithms, they are not analysis friendly, so they induce very complex stochastic processes. Markov chains whose transition matrices are not tractable in a sense with a exact analysis. And in addition, we would like to understand something about this process that is related to a global property. We would be interested in something that is called first hitting time of the optimum, something that runs over many steps, and very rarely it's possible to write down this first hitting time or expectation exactly. This is rarely possible. However, what we can often understand roughly is what happens when, from one step to the next one. When we are at some state in this evolutionary algorithm, how much progress do we make in one step? This is often possible to get some understanding of this local progress from one step to the next one. And drift analysis, in a nutshell, is the magic tool that allows us to translate statements on the one-step progress, on this local behavior, into a global statement on the running time, the first hitting time of the optimum. Please interrupt me if there are any questions. I'm going to show you a simple scenario, which is called...
Sorry, it's local in what?
So
clear.
Local means we find out something about what happens from one step to the next one. So local on the time scale.
But can the steps be big in some sense, or the steps are small?
So a time step would be around a generation in an evolutionary algorithm. So we could understand what happens from one generation to the next one.
No, I understand that, but one thing I could do from one generation to the next is just completely scramble all the DNA randomly.
Yes.
So there is a sense in which you're local in some... You're not going to allow that.
Yeah, local... Actually, in a local step, on the time scale, a very drastic change could happen. That's right. So local only refers to the time scale. So the scenario additive drift is about that you would like to analyze how long it takes until your process reaches some optimum. And in many cases, you can come up with a distance from the optimum. These are then random variables, discrete random variables in this case. So these xt are distances from the optimum. For example, in a bit string problem, this distance could show you or give you how many bits are wrong with respect to the global optimum. So let's say you are able to derive some bound on the local progress from one step to the next one. This is called drift. If you have a lower bound on this drift, an expectation, then I claim drift analysis enables you to get a bound on the expected time to reach the optimum. This is this t0, this is the time, the random time it takes until the process reaches an optimum, and we are interested in the expected value. So here's an example. Let's say we are at distance 10. With probability a half we go to 9, with probability a half we go to 7. So the expected change would be 2.
Is that second point ever a realistic thing that you might have?
On certain simplified problems, it can happen. That you have a local change. So of course this is just an example for illustration, but that you have small changes.
This is supposed to be for all t, the second one?
For all steps where we haven't reached the optimum yet. So this is the condition that is hidden here in this expectation. So
some very smooth function without local.
D represents discrete time.
D represents the progress from one step to the next.
Some discrete time, no? I mean, it's time.
It's a discrete time process, exactly. Okay, yeah.
But for what path? You probably have new path to get to the optimal position, no?
It's with respect to some distance measure. So we look into the search space and we simplify things by putting up a distance measure on the search space. So, question to you. So what is your guess? You start at distance n. In every step, you reduce an expectation by d. How long does it take in expectation to reach the optimum?
D over d, no?
N over d.
Okay.
Yeah, exactly. So, and this is somewhat surprising, a surprising result in the sense that this expected change here, the expectation, the randomness, it goes from, it goes then into the expected time to reach the optimum. So if it was a deterministic process, then this would be exact. And here it translates into the average time. And you also have a lower bound. So if you know that your progress from time t to time t plus 1 is bounded from above by d, then the expected time to reach 0 is at least n over d. Then you have a lower bound. So this is actually a rather old result from stochastic processes called, goes back to Wahl's inequality, but it was not used in evolutionary algorithms in this sense before 2001. And this is one of the major things that you would use to analyze such simple evolutionary algorithms. However,
by using, you mean trying to do mathematical analysis?
Yeah, mathematical analysis.
No.
Yeah, a mathematical analysis derive a bound like this algorithm takes n log n steps until it finds the optimum. This was one scenario, the simplest one. But one thing that is a little bit unrealistic here is that we assume that we always make a progress of at least d, no matter how far we are away from the optimum.
Exactly, because this with respect to what we spoke, what was here yesterday, whenever you get closer to the peak, you
Exactly. So this was a warm-up example. So what we often have in practice or in the processes we consider is a multiplicative drift. So still, let's say we start at n, a distance n, but now we have here that we reduce the distance from one step to the next by something that is dependent on the current distance, this expected conditional expectation. And the dependency is as follows, that we reduce by an expected delta factor of where we are. So this means large distance, large progress, small distance, small progress. Very natural. When we are close, then there are many things that can go wrong. When we are far away, there might be many things we could get right to make progress. So here's an example. This delta is the factor by which we reduce. This delta could be a half. So in expectation, we would get from 10 to 5. We would get from 8 to 4 and from 2 to 1. So let's look into this halving example. What would you guess if we have distance n in the beginning and half the distance in every step in expectation? How long does it take to reach the optimum?
Take forever.
exactly.
Yeah, it's a discrete thing. It's a discrete thing. It's a discrete thing. From 1, you would jump into 0.
No, by definition, it will take forever. You will never get there, by definition.
So it's a lower bound here.
If you're happy with being between
Exactly.
0 and 1, then log it.
Exactly. So and the rest, you're right. I abstracted away from this gap we have to have here between 1 and 0. So it's a discrete thing where when we are at 1, then we would have to jump into 0 in a non-increasing process. And that's correct. Up to terms, we have a result that is called the multiplicative drift theorem that would give us that the time to reach the optimum is basically twice the natural logarithm. And in general, the multiplicative drift theorem is like this. It tells us that the time to reach the optimum is the logarithm of the initial distance plus 1 divided by this factor, by which we reduce. So is this also a lower bound in general? So this means when you know that your multiplicative progress is at most delta s. So do things turn around as we had them before?
Omega log, no? Something like omega log as well, no?
No, exactly. They don't turn around because it could happen that we have an extreme case that, let's say, we have a process that from the current state with probability a half doesn't do anything, but with probability a half jumps into the optimum. Then in expectation, we would halve the distance. So this means in order to have a lower bound in the multiplicative drift, we have to assume more on the process. So then we have to assume that this process, it only makes small steps. Because in this scenario here with the halving, with probability a half into the optimum, probability a half don't do anything. We just have to wait for this super step, and the expected time to reach the optimum would be only 2. But in evolutionary algorithms, we often have such a concentration, and then we also get a lower bound of this type. So So this is a scenario that is called multiplicative drift, and that is much more typical than additive drift in the analysis of evolutionary algorithms, because of this fact that your progress is proportional to how far you are away from the optimum. So this was brought into the theory of EAs by Dörr, Johansen, Vinson, and Goldberg, and not too long ago, in 2010. So these are the tools. And in a nutshell, again, it was about try to bound the progress from one step to the next, and this will be translated into a bound on the time to reach the optimum. So I'll show you one warm-up example, how we can actually derive actual running time bounds using this multiplicative drift theorem. The algorithm is extremely simplified. It's a 1 plus 1 EA, which starts off with a uniform solution. The space are bit strings, and you have to minimize such a function mapping a bit string to a number. The function is called f, a pseudo-Boolean function. Only one individual, and mutation selection goes as follows. We take the current bit string x and flip each bit independently with probability 1 over n. So in expectation, we would flip one bit. And then if the new search point is at least as good as the previous one, then we take the new search point, the selection, analysis selection, otherwise we reject it. And we do this until some stopping criterion is fulfilled. A problem we consider here to show you how multiplicative drift actually gives us running time bounds is also, again, an extremely simplified problem. But this is how all this business started, with extremely simplified things. The problem is called 1 max. Actually, we are minimizing here. And 1 max problem, a problem on bit string, it just returns to us the number of ones in the bit string. So we have to reach the all zero string. So, and with multiplicative drift, we can now use this to do this stuff, that we analyze the progress from one step to the next. And everything is only dependent on the current number of ones in the bit string, because this algorithm is symmetrical, so it does not look at the positions. So our distance from the optimum would be the number of 1 bits in the current bit string, which we have to reduce to 0 in order to optimize this function. And this number of 1 bits, it could be a number between 1 and n. Assuming that we still have a 1 bit at some place, we can get rid of this 1 bit if this algorithm flips this 1 bit into 0 and does not flip the rest. And the probability for this, it can be bounded quite well. It's 1, so it is exactly for a single 1 bit 1 over n times 1 minus 1 over n to the power of n minus 1. The first thing is flip the bit, and the second term is do not flip the rest, and this is bounded from below by 1 over en, where e is Euler's number. So, and if you have s of these 1 bits left, then you can apply linearity of expectation, and you get this type of result that if your current distance is s, then you would reduce your distance by something that is your current distance times some factor, s over en. The factor is 1 over en. So in the example before, this delta was a half. But here it's much smaller. And then we can plug this in. Here it is again, the multiplicative drift theorem. The expected time to reach the optimum is the logarithm of the starting value plus 1 divided by delta. And plugging this in, we get a bound which is e n ln n plus a lower order term in the order of n log n. So running times, as you would see them in classical algorithms theory, running time we have for a sorting algorithm, for example. This is the kind of result we would like to obtain. Questions? So again, this was a oversimplified setting, but in fact we can use drift analysis to analyze more complex EAs, population-based EAs, like this one, without going into the details. The simple GA, where we have a population and we do not only have mutation but also crossover. We can analyze EAs on more interesting problems than 1 max, on combinatorial optimization problems, as you would consider them in computer science, minimum spanning trees, maximum matchings, and also harder problems, NP-hard problems like make-span scheduling. And more recently, drift analysis is a major a major tool to analyze EAs in noisy optimization. Since noise, it will make everything that was deterministic before in some sense stochastic. So an elitist selection will no longer be elitist in some sense, and then all methods that were used before for deterministic selection mechanisms, they do not work any longer. But drift analysis still works. Yes. This brings me to the second part. So I showed you the 1max before. And now a more advanced example in drift analysis, where I consider something that could be called generalized 1max, linear functions. And this is again an extremely innocently looking problem, but it's surprisingly hard to come up with good running time bounds. And while doing this, we get some consequences of the theorems, and these consequences can be summarized as follows. We get that in this setting, a mutation probability recommended in practice, 1/n, is optimal in theory for the whole class of linear functions. And we can also prove that it's basically on linear functions, it's best to take this oversimplified 1 + 1 EA. It doesn't pay off to use a population. It doesn't pay off to use a different mutation probability. It doesn't pay off to use stochastic selection. So the setting is a generalized 1x, as I promised, a linear pseudo-Boolean function. So the function value is now a weighted sum of the 1 bits, and the weights are positive numbers without loss of generality. And we also can assume that the bit of highest index has the largest weight. Then these weights might now be very different. In the 1max case, all of them are 1. And the question again is, how long does it take an evolutionary algorithm to find the optimum? Minimizing this, so how long does it take the algorithm to find the all-zero string? We can consider, in addition to 1 + 1 EA, another, even simpler randomized search heuristic called randomized local search, where the mutation is different. Mutation selects exactly 1 bit and flips it uniformly at random. So this can get stuck in the local optimum. The 1 + 1 EA, for comparison, it would flip each bit independently with probability 1/n, or more generally with probability p. So we can flip many bits in a step. We can't get stuck in local optima. So to find out a running time bound, remember with 1max we had this n log n. One might be tempted to think that we can just reuse this 1max result from before, so that the weights are not so important. Or if you don't know the multiplicative drift, but know computer science quite well, analysis of randomized algorithms, then you could think that this is the coupon collector problem. Coupon collector problem means that you have a set of things and objects you would like to collect. In each round you get independently 1 object, and you wait until you have all of them with replacement. The objects might arrive again and again. And what we have to collect here is 0 bits, so to speak. So the interesting part is that with randomized local search, which flips only a single bit in a step, we can apply these classical methods. So a randomized local search, it could do 2 things. It could flip 1 bit to 0, which leads to a better function value. The lower function value will be accepted. It could try to flip a 0 bit to 1, which leads to a higher function value. This will be rejected. So it will never lose 0 bits it has in the current bit string. Then the analysis is like on 1max for this randomized local search. But this is not the case for the general problem. So the 1 + 1 EA, it might do nasty things by flipping many bits in a step. For example, if we have a search point like this, the first n-1 bits, all of them are 0, and the most significant bit is 1. And let's say that the weight at this most significant bit outweighs all the other bits together. Then it could in principle happen that we accept a step that flips all bits in a step, resets the most significant bit from 1 to 0 and flips all the other less significant bits from 0 to 1. We accept this thing because the function value decreases. However, we have lost almost all 0 bits we had before. And this introduces a major complication to the running time analysis. And people, this is actually a long list of works by different people. They have tried to come up with increasingly improved running time bounds for the 1 plus 1EA on an arbitrary linear function with a standard mutation probability. So without drift analysis, you might be able to come up with a bound that is big O of n squared. But the first proof that we actually have the same type of running time, n log n, as with 1 max, this was only available in 98 and in the German version in 2002, and this was a proof of 7 pages, extremely complicated. People had been trying this before, so this was kind of breakthrough when this n log n bound was proved for an arbitrary linear function. And then people looked into this more closely. For 1 max, we had E n ln n up to lower order terms. So people were wondering, can these steps, flipping many bits, actually increase the running time compared to the 1-bit flips? So in the first answer given by Jägerskipper in 2008 was, they can, in principle, they might increase the running time, but if they do, then at most by a factor of 2. And then this gap was narrowed to 39%, and we also have a lower bound. So within the class of linear functions, the running time, it can vary by at most 39%. Maybe 1 max is the easiest linear function. On other functions, it might take a little bit longer. This was an open problem, but in fact, the answer is this is not the case. So on all linear functions, we basically have the same running time bound. So this is written down here in a bit more general flavor. So the running time bound is up to lower order terms, this guy here. It's e to the c divided by c times n ln n. Permutation probability c over n. So if c equals 1, we have the e n ln n bound, which we have for 1 max. We have it for all linear functions. Yes, and as said, this also depends on the mutation probability. So we could experiment with different mutation probabilities, 2 over n or a half over n. But it turns out that this guy here is minimized for c equals 1. So on every linear function, it's best to use the standard mutation probability. And this is a theoretical answer, so to speak, to the recommendation in genetic algorithms to use 1 over the bit string length as mutation probability. So probably I don't have time to give you all details of the proof, but I can give you some intuition and some interesting insights we get from this. One insight is that this e to the c divided by c, this is the waiting time until we have a mutation that flips only a single bit. So this whole process, this whole running time bound, seems to be governed by the steps that flip only a single bit. So the steps that flip more bits, they could, in principle, be detrimental, but in terms of the running time, they aren't, but they do not help either. So what we have to do to come up with its bound is to talk about distance functions. So within the class of linear functions, we might have two cases. We have many cases, and here there are two cases that are, so to speak, extreme. The 1 max case is that the function value is just the sum of the bits. All weights are 1. All weights are the same. We could also have a function called binary value. This is also a linear function where we have exponentially increasing weights. And here we have this phenomenon that the most significant bit outweighs all less significant bits together. So on 1 max, we saw before that it's not possible that the algorithm loses a 0 bit, even with the 1 plus 1 EA, because all bits have the same weight. If the number of 1 bits currently is s, then this number will only decrease. So the distance measured in 1 bits is non-increasing, and multiplicative drift works and gives us this bound. With binary value, we can have the extreme steps that make us lose on the number of 0 bits. One could consider the stochastic change of the number of 1 bits from one step to the next one. This is a random variable, this delta. How many 1 bits do we gain from time t to time t plus 1, or do we lose? And on a general linear function, this change, it can be negative, which is bad. We have a positive expectation in accepted steps, but this is too small in terms of an additive drift in order to get the bound we would like to have. If we just look into the expected change of the 1 bits, then we don't get the n log n bound. So what we have to do is we have to come up with a distance function. So do not measure the distance from the optimum in 1 bits, but into something that is a little bit more involved. For example, with the binary value, we should somehow favor the bits that have a large coefficients, have large coefficients in our distance function. So if we have an arbitrary linear function we would like to optimize, then the number of 1 bits as a conclusion is usually not a good potential function, which is the same as a distance function. When people were looking into potential functions, one potential function could be that we take the current f value. This is the weighted sum of 1 bits. This leads us to the multiplicative drift we would like to have, but in this multiplicative drift we also have the logarithm of the starting value. And the function value, binary value, is exponential. And the logarithm of something exponential, well, in this case it would be linear. We do not get this n log n. So the potential function, it should be not as extreme as binary value. If the weights of this function are steeply increasing, then it should a little bit compress the weights. And what was done already by Droste, Janssen, and Wegner, they came up with a potential function that always looked like this. The heavy bar, half of the bits, it got a weight of 2. The light half, it got a weight of 1. And in this way, we somehow favor in the distance function the heavy bits, the bits with a high coefficient. But this is not necessarily the best idea to use as a distance function if your function at hand is 1 max. If your function at hand from this class of linear function to be minimized is 1 max, why shouldn't we use 1 max as a distance function? If it happens to be binary value, we can't work with binary value as a distance function because the weights are too steeply increasing, but we might use more slowly increasing weights. And this idea to define the potential function, adapt it to the actual linear function, this is called adaptive drift analysis, introduced by Durr and Goldberg. So the new potential function follows this idea, looks roughly like this without explaining the details, but it has some exponential component, but the base is much smaller than 2. And it also has a component that allows us to obtain 1 max as a potential function if the linear function is 1 max. So what goes into the potential function is the mutation probability and also the original weights of the linear function. And then we get this behavior that if the function has steep coefficients, then we also have exponentially increasing coefficients, but with a much smaller base. If we have something like 1 max, then the potential function would be 1 max. We reproduce the original function in that case. Then we get the multiplicative drift. Multiplicative drift we would like to have. And what follows from this analysis is also that 1 max is the easiest linear function. So the optimization time within the class of linear functions is stochastically smallest. We get the lower bounds using this concentration property in multiplicative drift. We don't have large jumps. And we can also see how the running time varies depending on the mutation probability, P. It turns out that we have something that is called a phase transition. If the mutation probability is log n over n, it's still polynomial. If it is larger, then it's exponential, super polynomial. And the thing I mentioned before is that, in fact, we can identify a 1 plus 1 EA as the fastest algorithm within this class of algorithms where we can use a population of arbitrary size and we can decide to select any search point from the history for mutation. And mutation probability could be something which is bigger than 1 over n. And it turns out that a 1 plus 1 EA is the optimal algorithm within this class on linear functions. Good. Finally, the third part, I would like to talk about recent developments in drift analysis, which a little bit addresses this expected value of the running time. And as a consequence of this recent development, we might see that drift analysis is also useful for other purposes outside the theory of randomized search heuristics. So expected time, n log n for one max is fine, but an expected time could be misleading on multimodal problems. To have a problem like this here from the seminal paper by Carsten, Janssen and Wegner, a function called distance, which is basically a parabolic function with probability a half, you could climb up to a local optimum. You would initialize in the middle, roughly with the 1 plus 1 AA. So then it would accept with probability a half maybe to climb up the left branch, and with probability I have the right branch, but the left branch leads to a local optimum. And from this, you have to flip all bits in a step to jump into the global optimum. So we have a very skewed distribution with probability a half. We have exponential waiting time. With probability a half, we have basically one max, and we have polynomial time. So putting these two things together, law of total probability, tells us that the expected running time in this case would be exponential for the 1 plus 1 EA. But you agree, probably, this function is not difficult. We could just restart this algorithm when it gets stuck in a local optimum or run it in parallel, and every second trial of this algorithm roughly will make it climb up the right branch and find the global optimum. So an exponential running time is not necessarily an indication for hardness. We need more about the distribution of running times. And this is also something that is quite common in analysis of algorithms and stochastic processes. We would like to talk about concentration of measure. Looking into, for example, the number of 1 bits in the initial bit string. It is well known that this is very sharply concentrated around the expected value. In expectation, we have n half 1 bits. But there are tools called channel bounds that tell us actually that the actual number of 1 bits in a uniform bit string, it deviates from this expected value by no more than a square root of the number of 1 bits. So more precisely, the probability that it deviates by a factor delta times the square root is already exponentially small with respect to this delta. So this is a lower order term, the square root. Can we do something? Can we obtain something like this for our randomized search heuristics, evolutionary algorithms? And in fact, there is one such result that was already from the multiplicative drift analysis paper that shows that we also have a so-called upper tail bound for the 1 plus 1 EA. The probability that the 1 plus 1 EA on 1 max needs more than the expected value, significantly more, and this significantly more is an additive term of delta n, is exponentially small with respect to delta. So we have...
Is it derived directly from the Chernoff?
In this case, not. This is actually the multiplicative drift theorem by Joe and Goldberg. It has these tail bounds built in. So you use the multiplicative drift I showed you in the beginning, but the actual theorem, it does not only talk about the expected value, but also about the probability of needing significantly more than the expected value. So this was one side, the upper tail, and we did not have before a statement on the lower tail. And in fact, with drift analysis, with tail bounds, a recent development, we can also get the lower tails. And in many cases, we have a very sharp concentration of the running time around the expected value. And this tells us that, surprisingly, the running times are more or less deterministic, despite the fact that these algorithms are really heavily using randomization in every step at every bit. This could also be interesting from a practical perspective, because it tells us, well, we know quite precisely where we are with this algorithm at a certain point of time.
Additively around the expected running time, or
yeah, and we get, I will show you a few examples, and on the next slide we get a statement like this, that a deviation by a delta factor of something that is less than the expected time. So in a delta factor times a lower order term of the expected time compared to the expected time. This is exponentially unlikely. What we have to use here to get these tail bounds in general is something that is called drift analysis with tail bounds, a recent work with Christian Lehrer, where we first look into the one-step drift. We have a canonical potential function and bound the what is called moment generating function of this potential function. And maybe it's possible, maybe it's not, but if we succeed in bounding this moment generating function by something less than 1, then we have a tail bound. But one has to do the maths with the moment generating function. And one gets a very analogous thing for a lower tail. Look into the one-step drift in the expected value, potential function, moment generating function. This is the recipe, so to speak. And this gives us, for this 1 plus 1 EA on 1 max, coming back to your question, that, well, the expected time, it was basically E and ln n, and a deviation of more than delta times n around this expectation, well, above or below this expectation, it's exponentially small. And the same thing holds for all linear functions, and for other benchmark functions, we have similar statements. For, of course, simple functions which are unimodal. There we have, for example, that the expected running time is n squared, but the deviation of delta times n square root of n is already exponentially unlikely with respect to this delta. So finally, something quite different.
Before you go to something else, the example you showed where the expectation was NPN, but you try once again and you're likely to get so that you have results on also about the...
there actually we don't have a sharp concentration. So they have proved that with probability half we have exponential time. So we have a very skewed distribution. This is in some sense a bad distribution because it's very skewed and has half of the mass on an exponential running time and half of the probability mass on a polynomial running time.
No, but there are presumably more complicated versions of that, where if your number of times you're running in parallel is large, then the expected time is always dominated by the short.
Exactly. Then one
but the more presumably more complicated ones like that, which have which that's an interesting feature.
Very good point. That would be an interesting extension of this drift analysis with tail bounds to parallel runs of 1 plus 1 EAs or more complex things. It's a very good point. I think this is possible. But I mentioned I would like to talk about something that is not directly connected to evolutionary algorithms. Something that is very common in computer science analysis of randomized algorithms, recurrence relations, analysis of recursive algorithms. Recurrence relation is that the running time, let's say this T of n is the running time, can be written as a certain effort. For simplicity, it's 1 here, plus the running time on a smaller problem. This h of n is the size of a derived problem. The algorithm calls itself recursively, and we have this in Quicksolve, for example. But here it's a very simple recurrence relation. But the major thing is that this h of n, the size of the derived problem, it's random. A random number between 1 and n. And suppose we know the expected size of the derived problem. And of course, we also have to have a stopping criterion. If the problem is 0, then we do not have to spend any work at all. So this is a scenario that was considered by Karp. So what he did, he derived very clever tail bounds. The tail bounds, in this particular example, they would relate to a deviation above something that is the solution of the de-randomized recurrence. So he talks about what is the probability that the running time is a delta term bigger than something that is called U of n, and U of n would be the running time of the process in which you, instead of using a random problem size in the derived problem, use, well, the expected size, which you know as the actual size with probability 1. And he considers this scenario and also much more complicated scenarios and gets tail bounds. But of course, what we get here is a stochastic process again. We start off with problem size n, and when we go from time t to time t plus 1, the problem size will be, at the next step, the size of the derived problem, this h function that we have here in the recurrence. This h function, it could be anything. It could, for example, an expectation half the problem. And we are in the scenario of drift analysis.
Am I wrong that this probabilistic recurrence came up in the analysis of search algorithms?
I think so. I think, but in the CAR paper he considers many different applications. For example, also the quicksort. But there you also have this probabilistic recurrence. So I'm not sure what was the first application of this kind. The very natural thing is randomized quicksort. But this doesn't fit this structure. One application from the CAR paper is he uses his tail bounds in order to analyze a random combinatorial structure. So I guess all of you know what a permutation is. A random uniform permutation of n elements. Something that is, by the way, used in quicksort, randomized quicksort. People are interested in structures of such permutations. And one structure is cycles in permutations. A cycle is just a sequence of indices such that, well, one index maps to the next one in this sequence, and it wraps around. It's well known that each permutation can be written as a concatenation of cycles. And it can be useful to count cycles in the analysis of randomized algorithms. The number of cycles is a random variable. There could be one big cycle of all elements. There could be many small cycles of only a single element. Karp noted that the number of cycles, it can also be written in a recursive fashion. The number of cycles in a permutation of n elements is 1 plus the number of cycles in a permutation of h of n elements, where h of n is uniform between 0 and n minus 1. And then he gets a tail bound from his technique. The tail bound says that the probability that the actual number of cycles is significantly more than the binary logarithm of n is exponentially small. And this binary logarithm comes from the solution of this deterministic, de-randomized recurrence. Because here we have that the size of the derived problem is between 0 and n minus 1. So in expectation, we cut off half of the elements. So it's halving, 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 and this gives rise to a binary logarithm. Interestingly, this is not the expected number of cycles in a random permutation. So in combinatorics, it's well known that the expected number is the natural logarithm. So the binary logarithm is bigger than the natural logarithm. So in this sense, the statement tells us about something in terms of a deviation above something that is not the expected value. And then we have the sharp concentration, the tail, the sharp tail, exponential decreasing tail. And this, in some sense, it's necessary because the only thing that is used in Karp's technique is this expected size of the derived problem. And then this technique is optimal. In drift analysis with tail bounds, we follow a different approach. There, we can use the distribution of the stochastic process as we go from time t to time t plus 1. And in drift analysis with tail bounds, then we get a sharp concentration around the real expected value. Very similar to Chernoff bounds. But again, Karp's technique is optimal, assuming that you only know the expected size of the derived problem. And you have to spend much more effort in order to exploit the distribution. Obviously, this was just a proof of concept how drift analysis could work in the analysis of random recursions. a very simple case, and CARP considers much more complicated cases. For example, that this effort spent at the current level is not a constant, or that you have more than one recursive call, as in quicksort. And we do not know what to do here yet, in any case. Yeah, that concludes the third part and also my talk. So I was advertising drift analysis as one major technique for the analysis of randomized search heuristics, in particular evolutionary algorithms, and then considered one example, surprisingly difficult to handle, namely 1 plus 1EA on linear functions. Drift analysis gives us tight bounds up to lower order terms, and these bounds, they tell us that the whole process is driven by the steps flipping single bits, and the other steps flipping many bits, they do not help, but they do not harm either. For linear functions, we could prove as a result from this that the practical used mutation probability 1 over n is optimal in theory on this problem, and that this 1 plus 1EA, this greedy 1 plus 1EA, is the best thing to do on this linear function problem when you restrict yourself to algorithms using populations and mutation and selection, not talking about crossover. And the art in drift analysis can be to come up with a good potential function. Finally, the third part was about drift analysis with tail bounds, and drift analysis can give us tail bounds. And one thing that can be learned here, my hypothesis is, we have looked into evolution-inspired algorithms with computer science, from a computer science perspective. And this may be a promising thing because at least we have some idea that the techniques developed here, they might also be useful for problems from classical theoretical computer science. Yep. So this concludes my talk, and thank you for your attention.